Welcome back to the next video, everybody. This is the second to last video in this chapter. In other words, it's the final video before we are able to prove r equals t in the general case. All that's left to do is prove what we call Lemma Ihara. Please watch the last few videos if you haven't, and rewatch video 11.14 for notation. From there, we have finite sets of primes, sigma and sigma prime, in our set sigma sub rho bar being our plausibly modular representation, and natural maps that we called phi sub t from L prime sub t to L sub t, and phi sub h from L prime sub h to L sub h. To complete the proof of proposition 4, which is the thing that has taken us the most time to conquer, it now suffices to show the following, which we called theorem or lemma Ihara from a previous video. These maps, phi sub t and phi sub h up here, are surjective. So we're going to prove that today. Let's let n and m be natural numbers, and we'll let gamma 1 and m be gamma 1 n intersect gamma 0 m, and we'll denote by y1 and m and x1 and m the corresponding modular curves. We're going to require the following result. I'll call this lemma IH1, IH for Ihara. Let n be a natural number, and let p be a prime not dividing n. Then the following two things are true. If alpha and beta are the maps on the upper half plane, defined by tau maps to tau and tau maps to p tau respectively, then the map from h1x1npz to h1x1nz squared that sends x to alpha lower star x, beta lower star x is a surjection. That's the first thing we'll need. The second thing we'll need is that if n is bigger than 3 and L is a prime that's odd and not equal to p, then the following sequence is exact. h1y_npp squared z sub L to h1y1np z sub L squared to h1y1 of n z sub L. What are these maps? The first map here sends x to alpha 1 star x, beta 1 star x. And the second is the map that sends y comma z to beta 2 star y minus alpha 2 star z. What are alpha 1 and alpha 2 here? And what are beta 1 and beta 2 here? Alpha 1 and alpha 2 are just defined by tau maps to tau, and beta 1 and beta 2 are defined by tau maps to p tau, so kind of the same two maps from earlier. Okay, so we will not prove this. There's just kind of the original argument. It's quite readable. Part A is found in Ihara's on modular curve over finite fields. You can also see Ribot's congruence relations between modular forms, theorem 4.1. And then part B is actually a considerably simpler result. You can consult Weil's paper for that, Lemma 2.5. I sort of insist that you read Ihara anyway as part of your studies, because he's got quite a few results that contribute to Fermat's last theorem, and they're all quite readable. And then I'm not going to carry out the straightforward calculation of Weil's here. I will probably include it in my notes when I get to this chapter, ready for publishing on my website. Okay, but for here, it's not enlightening. We're going to move on. All right, and then we're going to need one other lemma. It turns out you can deduce lemma Ihara, the thing we're trying to prove, from lemma IH1, the lemma we just covered, using another result that I will call lemma IH2, and it says the following. Let O be the ring of integers of a finite extension of Q sub L. Let M be a natural number, and let H be a subgroup of Z mod MZ cross. Let T tilde sub O be T tilde sub Z tensored up to O, where T tilde sub Z is the subring of endomorphisms of M2 gamma 1M generated by the diamond operators, and the Hecke operators T sub R for primes R that don't divide M. And then let frac n be a non-Eisenstein maximal ideal. That's a definition from earlier this chapter. Then the localization frac n of the natural map from H1 of y1m_O to H1x1m to O is actually an isomorphism. So in other words, you take this map, it's a natural map here, you localize at this ideal, you just actually get an isomorphism. And then the map from H1x1 of m_O to H1xh m of O, remember from this subgroup here, you can produce a modular curve. We've known that since like chapter 3 of these notes. This natural map, after localizing at frac n, is a surjection. Okay, let's just recall, what does it mean for a maximal ideal frac n to be Eisenstein? It just means that the p Hecke operator is p plus 1 mod frac n for all p that are 1 mod frac n. Okay, so let's look at the proof of lemma IH2 real quick. The first part is checked pretty easily by just showing that h1y1mz to h1x1mz is surjective, and that t sub r equals r plus 1 on the kernel for primes that are r equals 1 mod m. For example, this is checked in the Diamond-Darman-Taylor notes, proposition 4.13c. It's straightforward. Okay, we won't delve into the details now. because we're actually going to be revisiting this very concept more later when we jump into the next chapter, which is the proof of R equals T in the minimal case. And then the second part of lemma IH2 is shown by checking that the Galois group of Q acts trivially on the co-kernel of the natural map from the Tate module T sub L of J1M to T sub L of JHM. You can see, for example, if you want more details, the Shimura group of J0N proposition 6. And then you can easily check that for an odd prime L, the representation rho sub frac M is absolutely irreducible if and only if frac M tilde is not Eisenstein. This is proven in a number of places. The easiest proof that I know of, and I think I will include the proof of this in my notes that are actually for publish, is DDT lemma 4.12. Okay, and so that's the proof of lemma IH2, or just kind of a sketch or an overview of it. So now how do you deduce lemma Ihara from these two lemmas? Well, first of all, it definitely suffices to consider the case where the bigger set of primes in question, sigma prime, is just the smaller set of primes, sigma, union one more prime, p. And then we are only going to discuss the actual difficult case where p isn't equal to L. There's a much, much easier proof that follows similar logic when p is L. Okay? Let's let n equal n sub sigma, which is notation from this chapter. And we'll let n prime be np squared. And we'll let frac m and frac m prime be as usual from, for example, videos 11.13 and 11.14. This makes frac m prime a maximal ideal of T prime sub O, where T prime Z acts on S2 gamma 0 n prime, just to be clear. All maps in the following argument are going to respect the Hecke action of T tilde double prime Z, the subring of endomorphisms of M2 gamma 1 NPP squared generated by the diamond operators, and the Hecke operators T sub R for primes R not dividing NP. And then finally, we will let frac n be the preimage of frac m prime in T tilde double prime sub O, which is just T tilde double prime sub Z tensored up to O. Okay, so that's just notation, basically. Okay, so here's the proof, and this is a really neat proof. I like it. What you do is you just keep abusing these lemmas over and over and over again. So first, if you look at part B of lemma IH1, it shows that H1Y1 NPP squared O localized at frac n to H1Y1 NPO squared localized at n to H1Y1 of n O localized at n is an exact sequence. You take that and you apply lemma IH2 part A to find that H1X1 NPP squared O localized at n to H1X1 NPO squared localized at n to H1X1 NO localized at n is exact. Then you go to lemma IH2 part B. You apply that to this result in the case where m equals np to show that H1X1 NP squared O localized at n to H1X1 NPO squared localized at n to H1X1 NO localized at n is exact. So we keep bouncing around between different parts of these different lemma IH1 and lemma IH2 to actually get that various sequences are exact. And I've checked all this. The applications are pretty straightforward, actually. Okay. Then you use lemma IH1A to show that the map H1X1 NP squared O localized at n to H1X1 NO cubed localized at n. And this map, just to be clear, sends x to alpha lower star x, beta lower star x, gamma lower star x is surjective, where alpha and beta were already defined, and gamma is defined by tau maps to p squared tau. Okay, so this map is surjective now by part A of lemma IH1. Then you use lemma IH2b again, now with m equals n, which is not how we used it before, to conclude that H1x0 np squared O localized at n to H1x0 NO cubed localized at n is surjective. And the result now follows immediately by just localizing at frac m prime. Okay? So that's how you deduce lemma Ihara from lemmas IH1 and IH2. It's a pretty fun little cute argument. It reminds me a lot of how Ribot's theorem is proved. Not necessarily in complete spirit, but this idea that you've got these preliminary results involving exact sequences and you just keep using them over and over and over and over again until you get what you want. Okay, so we are done finally with all of the prep work after all this time needed to prove R equals T in the general case. We will do that next video. That video will be actually quite easy compared to a lot of the videos leading up to it, because a lot of the hard material, quite frankly, has been covered now. And then starting the video after that, we will move into R equals T in the minimal case, which is a whole different can of worms. So thanks for watching, and I'll see you then.